Thank you for that nice introduction, and also thank the organizers for the great honor of me coming here. I've never been to this conference before and being given the opportunity to speak. So what I would like to discuss this afternoon is some work we've been doing over the last few years trying to explore a new type of diffractive interface which we've been referring to as Fourier surfaces. But before I get into that too far, I want to give an introduction and just to remind you that in optics we only exploit a few key effects. We have reflection in devices like mirrors and filters, we have refraction in devices like lenses, prisms, and fibers, and then we have diffraction. And Sommerfeld once described diffraction as basically anything that's not reflection or refraction. And this gives rise to devices like gratings and holograms. And if we want to describe all of these effects under kind of a common umbrella, there are different ways that one can do that. The way that I'm going to do that is in terms of momentum. And so we all know that if we have a plane wave propagating, we can describe it in terms of its wave vector k, which for a plane wave just points in the direction of propagation and has a magnitude of 2 pi over the wavelength. But more importantly for this talk is we also know that k is directly proportional to the linear momentum of the photon. So k in this talk is going to be a stand-in for momentum. So if we then imagine this light wave impinging on a flat interface between two different materials, we can then consider the in-plane momentum, so the x component of the momentum. And for reflection, we know that angle of incidence equals the angle of the output. This is simply to conserve the in-plane momentum. Similarly, for refraction, we know if light enters a material with a higher refractive index, that it bends towards the surface normal. And again, this is simply to conserve the in-plane momentum. So in-plane momentum in these cases is conserved. That's not surprising because nothing interesting is going on in these structures. They're basically totally boring in X or invariant in X, so this makes sense. And of course, it becomes more complicated if the structure is then, the surface is then structured, and this is what gives rise to diffraction. So in a structured interface, the classic example is the diffraction grating where we have grooves that are periodic in X. Maybe I'll move over here. And well, maybe I can't. And the beam direction, we know when it hits this periodic structure, will be altered essentially due to interference or what we call diffraction.